All right, I'll begin with a word of prayer. Heavenly Father, we thank you for this morning. We thank you for your grace and mercy to us. We thank you that you have loved us even while we were sinners. And of course, we're still sinners. We thank you, Lord, that your righteousness covers us. We don't have to rely on our own righteousness. We know our righteousness is like filthy rags, and we know that we only have salvation through you, Lord. And we just thank you for this day. I just pray you be glorified in what we do here, that we would just draw our ideas together so we're ready for the test Thursday. In your name I pray, Lord Jesus. Amen. Oh, wait. Well, questions? Any questions? Read through the list. Let's see here. Let me put the list up. Step number 1, find list. Step number 2, take list and put it in anything except for Blackboard. Notepad's probably not going to be the best. Come on, where's my stupid, did you guys see? Yeah, that's what I'm looking for. Oh, is it the top? It's painful. Oh, yeah, that one.
The one right above the notepad. So,
yeah. I did that, didn't I? All right, let's see here. Try one here. No, that's not right. What? Well, this is just frustrating. One page. Still not what we want. Come on. How can I make it? I'm trying to make it bigger because it's like it's. I guess you can read this, huh? Fine. Ah. I swear. Fine. We'll just go with this. Okay. So now you have questions. Oh, now we'll see all my spelling mistakes. Exciting. Let's see here. Fundamental. 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 Let's see here. So, any questions?
Can you go over some Lagrange stuff, like conservation of energy?
Yeah. Actually, it's a good question. You know, hopefully that's it. All right, so I will post this at 5 today. All right. So your question is Euler-Lagrange. Let's see here. So like problem 68, for example, we have m over 2 x dot squared plus y dot squared minus kx squared plus y squared. Just to be like a thing in two dimensions, like it'd be like a spring that was in the plane and it was free to go any different which way, like a spring attached to a central pivot point that could go around, and the length squared, the distance squared of the spring would be x squared plus y squared. And so this, you could actually think of as like the equation for a spring in the plane with a mass attached to it. So basically you just figure out what are my dependent variables, and you take the derivative with respect to the independent variable of the partial derivative of the Lagrangian with respect to the velocity of the dependent variable. And
my question is like, how do we know like which is dependent on t? Where do we get that from?
It just depends on the problem. I mean, so if I have for example, the arc length integral, square root of 1 plus dy dx squared, dx, then this being the Lagrangian, or we were calling it f at that point. Then in this case, you'd have d dx of partial L partial y prime is equal to partial L partial x, right? Whereas, yes, it would. Thank you. Sadness. On the other hand, if I had s is equal to the integral of the square root of x dot squared plus y dot squared dt, which I could do for that'd be the arc length of a parametrized curve in the plane. Then I have two dependent variables. I'll have two Euler-Lagrange equations, one for x and one for y. In this case, I would have d dt partial L partial x dot equals to partial L partial x and d dt partial L partial y dot partial L partial y. I mean, of course, those are both 0, but in this thing I just made up. But so it's really a question of context. Oh, sorry. I keep changing my mind. Now, I mean, here's a guide. If I give you the action, in other words, the integral, which the variational principle is built around, right? We take the variation of some action, which for us is built from some integral, and we're integrating some function we call the Lagrangian, right? So whatever the integral is taken over, that's your independent variable. So here are the integrals taken over dx, so the independent variable is x. Here are the integrals taken over dt, so the independent variable is dt. And then the dependent variables are, whatever. Well, that varies from problem to problem. It could be x, it could be y, it could be x, y, z, it could be r and theta, it could be q1 and q2, it could be, that's the beauty of the method is we can essentially choose arbitrary dependent variables on time or something else. Like I found personally, I'll show you this. Here's what I was talking about, Nathan. For the geodesic problem on the cone, I started by thinking, what's the metric in spherical coordinates? Well, that's the metric in spherical coordinates, and then for a cone, we have d phi equals to 0, right? So because phi is equal to a constant, you choose phi equal to a constant, that's the equation of a cone. And so the metric reduces to d rho squared plus 3/4 rho squared d theta squared for the particular cone we're looking at. And so then my knee-jerk reaction is I love parametrized curves so much, I just introduce a parameter time, and so there's my action, and then I can find other Lagrange equations from that, right? Well, that's great, but then I can't solve these. So I'm like, oh, dumb. If I just ask you to set up the differential equations, who cares? You do it parametrically or do it the way I'm just about to show you, who cares? I mean, either way, you've set up equations whose solutions, minimize the action which we're given. So if I was just asking to set up equations whose solutions are geodesics, great, we're done. Wonderful. However, if you actually want to solve them, this is kind of, well, I don't know. I did some stuff, and I got closer to what I feel like is a solution. And I think I can chase this down, and I think I can find parametric solutions to this if I want to, but I just got tired of it. So I changed gears and decided to use one of the spherical angles as my parameter. Basically use t equals to what? Basically, I'm thinking t is equal to theta in some sense. In other words, I want to look at rho as a function of theta, right? And so from that perspective, it becomes more like this, right? There's just one dependent variable. And so having done that, I then have this Lagrangian rho prime squared plus 3/4 rho squared. And this gives me the Euler-Lagrange equation, 3/2 rho equals 2 rho prime prime. And that I can solve because that's a constant coefficient second order ordinary differential equation which has Cauchy-Simpson solutions. Bam, done. Now, that said, I don't know yet. I haven't finished. I mean, my ideal solution to this problem would complete the thought to show you that in fact that is what you'd get if you took the cone and laid it out flat as a piece of paper and you looked at the line on the paper, then that line has become this curve. Now I haven't fleshed that out, right? That would be the full, in my opinion, treatment here. I haven't done that, but the other question I asked you to find solutions to are geodesics to x squared plus y cubed plus z to the fourth equal to 1. I'm glad I didn't ask you to find the geodesic because so there's two ways to set this problem up, right? The one way would be just to put in the constraint at the start. In other words, assume, basically build in that equation x squared plus y cubed plus z to the fourth equal to 1 at the level of the kinetic energy, basically. And so I differentiate that at solve for x dot. I get this monstrosity for x dot. And then I can plug that in, and here's the Lagrangian y dot squared plus z dot squared. That. And then if you were to calculate the time derivative of the partial derivative of L with respect to y dot, and the time derivative of the partial derivative of L with respect to z dot, and set it equal to partial L partial y, partial L partial z, those would be the Lagrange equations. The solutions to those would be geodesics to this x squared plus y cubed plus z to the fourth equals to 1 equation surface. Ugh. Oh, what? Hey, I plugged you in. Oh, I tell you, there's a saboteur in here. Someone's trying to mess up our fun.
So you don't go over it all, but you probably want to plug it in over.
Well, yeah, I know, but I'm too lazy. So you can laugh at me when I trip. But you're probably right, though. So
There are a few times in this class I wanted to say that. But
this is obviously not fun, right? And so if you use the method of Lagrange multipliers at the level of Lagrangian, it gives you a much nicer system of equations to try to hack through if you were to hack through it. I kind of like the organization of this approach. I take the free Lagrangian and then I just adjoin a constraint with a multiplier like that, and then I have to solve these 4 equations. The last, or the Lagrange equation, of course, is kind of a silly one. It's not a dynamical equation, right? And that's the auxiliary variable, the lambda, enters algebraically. That's kind of the nature of an auxiliary variable. But anyway, so those would be another. I mean, either the awful that was at the top or this would be geodesic equations. Does that make sense? I mean, yeah.
So what do you do with lambda? Like after you find it, you just set it equal to 0, or like how do you get rid of it when you actually?
Oh, these? I would solve for lambda. I would probably try to solve, maybe well,
Oh,
yeah.
so get lambda in terms of x, y, z.
Yeah, you've got something like x double dot over 2x is equal to y double dot over 3y squared is equal to z double dot over 4z cubed here. And that's probably amenable to some sort of hidden art of differential equations, which, if this was a course on variational calculus, I would show you the trick to solve this, but I have hope that that could be solved. I mean, you see that that's kind of a nice set of coupled differential equations. There's hope for that. It's kind of like the method of characteristics kind of problem. But I'm just showing you how to set them up. I'm not showing you how to solve all these. That's harder. Yeah. I mean, good grief, I can't even solve. Well, I can solve some of these things, but this problem 68 isn't too bad, right? How do you show energy is conserved? What does it mean for something to be conserved? It means that the derivative of it's 0, right? So for this one, to show that the derivative of it's 0, I mean, there's different. I mean, I can actually just take the derivative of e, and if you put in the equations of motions and these terms cancel and you get back 0, is one way. So, yeah. The geodesic on the sphere, I don't know. I've got it down to this integral, but I don't want to do that integral at the moment. Whatever. Problem 70 is very simple. Those are the Lagrange equations for this one, right? You know, mr double dot is mr squared theta dot squared plus dg dr. And then the other one is ddt of mr squared theta dot. Because theta is what's called an ignorable coordinate, there's no theta dependence, explicit theta dependence in the Lagrangian. Hence, the partial L partial theta term is 0. And in fact, the second order Lagrange equation is precisely the conservation of angular momentum, so there's almost nothing to do here. 2 lines. I know it's confusing. I've asked all these like difficult, like several day homework problems. These shouldn't be that easy, right? I was trying to take it easy on you guys before the test. If I'd been smarter, I wouldn't have asked the geodesic questions. I should have remembered that those are truly awful. They are truly awful.
We're only supposed to like find like the equation. We're not supposed to solve anything.
I think the way I asked it was to find the geodesics, which suggests that you have to solve the differential equations. The one I just asked to find the differential equations, but the other two I said find the solutions, which is much nastier.
66 is find the geodesics.
Now, yeah, 72 is actually not. It's 72 is a great example. It's just the how beautiful this whole construction is and how neat it is. You can solve problems like this. A pendulum on a pendulum. You just have to write down coordinates and work it out. And basically, I don't know why I've got R1 and I've got an R1 and R2 here. It's kind of unnecessary because they're just the constant L1 squared and L2 squared. So don't make too much of that. Although, I suppose if you let L1 and L2 be variable, you could do that. You could have pendulums of variable length, right? That would just add some L1 dot terms and L2 dot terms, and you'd have 2 more dependent variables, but you could do it. Pretty much. Just a few more derivatives. I mean, I couldn't solve it any more than I can solve these without a lot of work. And so here's the Euler-Lagrange equations for 72. But anyway, so let's stop talking about this. This is really not the biggest part of the test. So, let me just go back to the start of this, though. The start of it's more important. I will actually probably want you to know about quadratic forms, right? And so here's the rules. I might ask you to calculate a 2x2 on the test, explicitly find eigenvectors and eigenvalues for a 2x2. But for a 3x3, I probably wouldn't ask you to find the eigenvalues because it's just, unless I conjure up some kind of silly example where it's really just a 2x2 in disguise and not really a genuine 3x3. They're just nasty, right? So 3x3, I would probably not ask you to find the eigenvalues of a 3x3 matrix. But I might give you a 3x3 matrix. I mean, there are ways I can ask the question without actually making you do that calculation. As I kind of reveal in these homework problems. Any questions about this one? Okay. I've talked about this problem individually, most of you, the next one, and there's a way you can make this problem so much harder than what I intend. I really do mean in this one that you find the eigenvalues, 9, 10, and 42, and then you write down the formula in eigencoordinates. And so once you know this, the spectral theorem tells you that in eigencoordinates the formula is just this. Or, I'm sorry, my problem, I said y1, y2, y3, so the eigencoordinates is this, right? 9y1 squared plus 10y2 squared plus 42y3 squared. Now, of course, the spectral theorem doesn't directly tell you the formulas for y1, y2, and y3, but those are easy enough to figure out if you follow the method of the previous problem. Again, not an appropriate test question because it's just so much computation. It would eat a half hour of our time to really go through that for a particular example. Unless I was somehow to play with the games that I show you in problem 59, for example. I don't know. But so 58 and 59 are linked, right? So basically the point here is in 58's easy. Here's you write down the matrix, right? Plug it into your favorite eigenvalue calculator, and then the spectral theorem tells you the formula in eigencoordinates is that, right? But problem 59, I actually show you where I came up with that differential, with that quadratic form. What I did was I constructed A by picking the basis I wanted it to have. I just chose that as a basis. And then I decided I wanted to use eigenvalues 3, 6, and 8. The reason for that is simply that I wanted no square roots in my matrix. And I know if I use 3, it'll cancel the third that comes from multiplying root 3 over root 3. And I know that if I use 6, it'll cancel the root 6. And I know if I use 8, then it will get rid of the half, which comes from this in the formula down here. Right? So I knew that would give me a matrix with integers, with nice eigenvalues, with a relatively cool orthonormal basis. And so this is how I can make up examples that have these nice properties. See, I'm showing you how I make examples in this problem. Don't tell linear algebra about this. But you see, the examples you can come up with are kind of boring in some sense, right? They have to be they end up being symmetric matrices. They only have real eigenvalues. So it's in the world of all possible eigenvalue examples, it's somewhat limited. But here symbolically is why that works, right? Because if I multiply v1 times that expression, these dot products are only 1 if you got 1 and 1, but that's 0 and that's 0. And this is 1, but that's 0 and that's 0 because v1, v2, v3 is an orthonormal basis. So these dot products are either 1 or 0 depending whether it's the vector again or not the vector, which shows you why this formula has to produce eigenvectors. Now, of course, I actually calculate that. And I asked you to actually calculate it explicitly for the matrix. I didn't say I gave it for specific numerical vectors for a reason. I wanted you to connect with the previous problem. That was the point here. But the page before shows you that it's rather quite general. It's not about these specific vectors and these specific numbers. One of the interesting things about these matrices, what's the rank of 1, 2, and 3? One. See, I'm building these matrices from a single vector, right? So it's like it's a linear combination of 1, 1, 1. It's a linear. It's every column is a scalar multiple of either 1, 1, 1, 1 minus 2, 1, or 1, 0 minus 1, right? So they each have rank 1. If and I don't know. It's interesting. These are projection matrices onto the eigenspaces. I digress. We don't need all that for this course so much, but make sure you can do something like problem 60. It's so simple, right? So basically, you just have to compare the given power series expansion to the Taylor expansion that's known, and just match coefficients, right? So I can see from that 3, 3, 4, 4, 6, and 14 just by comparison. And notice that there is one little pesky detail. There's a half on the double derivatives, but there's no half on the mixed derivative. And like the binomial theorem happens at higher order. So, but anyway, I'll just ask to. I think I'm only going to ask to second order on the test, so you don't need to worry too much about higher order stuff. Are you guys comfortable in 61? Let me work a different problem than 61. How about this? What if we wanted to find the expansion about, let's say 1, 0, 2 of, I don't know, how about f of x, y, z equals to e to the x times 1 over 1 plus yz. Oh, I'm going to regret that. There, it's better. So basically the name of the game here is, first of all, you must resist. You must resist the temptation, the standard temptation of Calculus 2. Once I know the Taylor's theorem, I must use it without thinking. No! You must not use Taylor's theorem without thinking, because that would be a truly awful thing to calculate partial derivatives of that, even to second order for all the possible derivatives involved. What is much, much easier is to use substitution into known series. Right? So like e to the x, well, I know what that is. That's 1 plus x plus 1/2 x squared, right? And let's say I'm just going to take to say second order for the purpose of our discussion here. And this is what? That's 1 over 1 minus u, which is 1 plus u. Or let's say 1 plus u is 1 minus u plus u squared plus dot dot dot. Geometric series, right? So this is 1 minus y times z plus z minus 2 plus y squared times z minus 2 squared plus dot dot dot. And then you can just multiply out and keep terms. So I got a 1, and then let's see here. What's my next term plus what? I guess the only term to quadratic, I guess I got 1 plus x plus 1/2 x squared. That's it for the lower order stuff, right? And then what's quadratic? I think that's the only quadratic term, right? Oh, yeah, you said minus y times z minus 2. So I'm just trying to collect things order by order. Order 0, order 1, order 2. Anything else order 2? I don't think so either. Now order 3 would be minus x, y, z minus 2. Oh, yeah, thank you. And I'll just stop there because I'm out of space. That's kind of fun, right? Because I can tell you from this immediately that the f, x, y, z derivative at the point 1, oh man, why'd you guys let me do that? Come on. You guys let me write so much. Golly. Now I gotta do this. Thanks a lot. 0. No, you cannot do that. 2 is apparently minus 1. Well, again, I said I wouldn't ask about third order, so maybe this is a little bit outside the edge of what I'd want to ask about. But I'm just saying you can look. That doesn't count. I didn't fall. That doesn't count. I did not fall.
You see us laughing, right? Yeah.
Fine. Hope you're happy. Still wanted the screen to go yellow again. Now, yeah, there is a standard. Let's see here. More interestingly, or perhaps less interestingly, f y z at 0, 0, 2 would be equal to what? Not minus 1, because there's a. Oh yeah, you're right, minus 1. Thank you. I was going to say -2, but that's wrong. That's only for like, this would say that fxx at 0, 0, 2 is what? It's 1, yeah, okay. In fact, there is a standard thing we could do. Basically, just take e to the x and say that's e to the if I wanted to center it at, say, 1, 0, 2, whatever, then I would take e to the x and replace it with e to the x minus 1 plus 1, which would be e times e to the x minus 1, which is e times 1 minus 1 plus x minus 1 plus 1 half x minus 1 squared, et cetera, et cetera. So we'd use that trick in conjunction with what I already wrote to center around that point. All right, well, anyway. So what I'm saying is all the stuff we did in Calc 2 you could still do here, of course. But now that said, once you get through the jibber jabber here of the substitution of the series, what's more interesting is we have this quadratic piece, right? And then, well, this quadratic piece, and then, right, this quadratic piece. And then you can ask the question, is it a saddle point? Is it a critical, first of all, is it a critical point? Then what's the nature of the critical point? Is it min? Is it max? Is it saddle? What kind is it? So if I look at this, it is a critical point. There's no first derivative terms, right? There's no x, y, z, so the gradient at 0, 0, 0, 0, 0, 0. And the Hessian, the matrix of the second derivatives here, you can read from what I have up there. It's 0, 0, minus 1 from this. So those two, let me give those two terms. A 1 from the y squared, and, oh, this doesn't count. That's quartic, right? So that's it. And then to calculate the eigenvalues, I just do the usual eigenvalue calculation, and there it is. So I guess I might ask you to calculate, if I was going to ask you to calculate the determinant of a 3 by 3, it would have to be like this one. I think that would still be fair, right? Can I go back on my word a little bit and say include this in the test, maybe? I think this wouldn't be too mean, right? But yeah.
For the Hessian, wouldn't like FYY be 2 in that case? Like,
Oh, curses. Yeah. Oh man. Yeah, you're right. Ah! No! Oh man. My parents are at my house right now. I blame my parents. Yeah, I guess I could fix it. All right, it's fine. I'll see if I can fix it. All right. Oh, it comes out to the same. You got the same answer? Funny. I think that's accidental, but yeah. I've made a few errors there, so maybe they were canceling. An even number of errors. Problem 63 I was pretty happy with. I really like this idea of differentiating under the integral. It's really, man, I think it's a really powerful idea, isn't it? So, did you guys find these? 63? Well, I don't,
the one that we just did.
oh, I don't know. 60. Oh, did I not do 62? Uh-oh.
Okay, I was just making sure because I was going to say I didn't get solid points.
Where is my 62? Oh no, Joe. You mean to say I haven't solved 62? What was 62?
Find and classify critical points of.
Oh, yeah. Tell you a dirty little secret here.
I mean, it's not that hard of a problem.
See here. Dum 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 dum. see, here's some old homework problems. Let's see here, what do I got? Man, that problem was a beast. I thought I'd come up with this really slick, easy problem, and then this happened. But this might look familiar to you. So if you look at problem 45 of 2013, mission 5, there it is. So what did you get? Now, when I've assigned this problem before, it is invariably the case that students miss 1 or 2 of these critical points. Almost no one gets all 3 of them for some reason. I don't know what it is. And different students will get different ones too. It's fun. Like if I have a class, I had like 8 people taking it last time, right? And like so, like Johnny, you got 0, 0, and 0 minus 1, and let's say Jill got 0, 1, and 0, 0, but nobody got all 3. And they just, it's very, very disconcerting, kind of. Anyway, any questions about that one? You just kind of have to fight through the algebra. You need both partial x, partial f, partial x, and partial f, partial y to be simultaneously 0. So if you just chase down those possibilities systematically, you should come to these 3 points. 0, 0, 0 minus 1, and 0, 1. Yeah. Right, let's see, how did I do it? This is not a good way, right? It's just, I was lazy. I just used the Taylor series. Yeah, I think it may be faster to do the expand about a point trick. I'm not sure which is more efficient here. Sometimes it's not always the case that the expand about the point trick is like full of awesomeness.
I just didn't talk through method.
Well, anyway, there's that. This problem is really cool. I didn't assign it to you guys, but it's really pretty. Anyway, I digress. All right, let's go back to what we're doing. So again, just to reiterate, for linear algebra, I want you to know trace, I want you to know determinant, I want you to know matrix algebra, right? You don't have to worry about coordinate change for this test. I'll get back to that later. We'll be doing lots of coordinate change soon. I do want you to know eigenvalues and eigenvectors. I do want you to be able to define an inner product, right? If I define some quote-unquote operation, I can ask you a question like, is this an inner product, right? And you should be able to either prove that it is or give me something about it that makes it not be an inner product, right? Here. I say xy is equal to x1, y1 minus x2, y2. And here x and y are elements of R2. Is this an inner product? There you go. So you just show me, well, 0, 1, 0, 1 is equal to minus 1, which is not greater than 0, so it's not positive definite. Yeah. What are the axioms for inner product? What do you need? It's bilinearity. You're thinking of the norm. Bilinearity, what's that? Positive definite and symmetric. So positive definite is that x comma x is greater than or equal to 0, and xx is equal to 0 if and only if x is equal to 0. That's positive definite. Now the norm, right? I don't know where she left it. I don't. Poor Bradley. You can kind of see it. I'll zoom in a little bit. Now the norm, of course, that we want the absolute homogeneity, all right? So we want the norm of Cx is absolute value of C times the norm of X, right? And what else do we need? We need, norm of X greater than or equal to 0, and the norm of X is equal to 0 if and only if X is equal to 0, right? What else? Triangle inequality, right? Now, what inequality do we know for an inner product? But it's not part of the axioms, right? Yeah, we know Cauchy-Schwarz for inner product. One of your homework problems is actually to prove that. But that's not part of the axiom, right? That's a derived consequence of the axioms. And was there anything else for the norm? I think that was it. Yeah.
Positivity, homogeneity, triangle inequality.
The more basic thing, of course, here is that what? The inner product, right, is a mapping from V cross V to the reals, because we're looking at real vector spaces, okay? And now you could talk about an inner product which was a mapping into the complexes or something else, but that would be a different thing. We're talking about real vector spaces. Our inner products are real valued, at least for now. And the norm, on the other hand, is just a mapping from V to the reals, right? Or you could, of course, safely replace that with non-negative reals. So, a real softball question would be something like this. Is this an inner product? So you'd be like, well, no, because it's a matrix. And a matrix, unless n and n are both 1, no, this is not an inner product. I mean, in the one-dimensional case, is it an inner product? Yes, it's the dot product in one dimensions. But anyway, that's a stupid case.
So for inner product, we're simply looking at positive definite groups that we could use as part of definition.
Yeah, inner product, we want positive definite, and we want bilinearity is the big one. So I probably would have positive definite if I did this. Let's see, if I did something like VW is equal to V1 squared W1 squared plus V2 squared W2 squared. I'm pretty sure I'd have positive definite. It's definitely non-negative, and it can only be 0 if all of those things are 0, right?
By linearity, that's like
But this is
product of like ax plus by times something that's like
right.
a times the one inner product plus b times the other inner product.
It's that we have linearity in each slot is the kind of like the easiest way I know to say it, right? If we just freeze one of the entries, we have linearity in the other. So there's linearity in the first slot. That's not going to be true for this formula because of the squares.
So that is essentially our one part for
Yeah, I mean, there's plenty of other things. Like, for example, we have the Frobenius norm on the matrices, right? So let's talk about something that's true. So that would be the trace of AB transpose, right? And so if I have like CA1 plus A2, B, then that would be the trace of CA1 plus A2, B transpose, right? And so this is what I'm talking about when I want you to know the properties of trace and stuff. Because if I ask a question like this, I don't want you to be like floating, not knowing what trace is, not knowing that trace is linear and that you can do these things, right? I want you to be able to use these properties of trace and transpose. Well, we haven't used transpose yet, but that is what? That's C A1b plus A2b. So there's linearity in the first spot. And then if I have symmetry, right? And two of you had this, I think, right on. The other three were, no, three were fine.
This is a homework problem.
Yeah, this is homework, exactly, indeed.
Which homework problem?
Oh, goodness gracious. I'll tell you in a second here.
Something. Is it this one?
So the way I mean, here's the laziest way to do this. I mean, now Joe, the way you did it was to stone cold find a formula for the trace in terms of the components and write that it was the sum of the components squared, which was fine. Oh, maybe not this part. I'm thinking of the positive definite aspect, sorry. But to prove symmetry, the trace of the matrix is the trace of the transpose of the matrix, right? The trace of a matrix and the trace of its transpose are the same because the trace only is based on the diagonal, and the diagonal is fixed under transposition, so it doesn't change. And then socks shoes. So that's the kind of thing I mean when I say that I want you to know matrix algebra. I want you to know things like that, right? Mostly that. And of course, that's what.
What do they call the socks shoes? Is that like
'Cause
only, or is it indicated?
it's a well-known colloquial saying for this. It's like, you know, how do you put on your first you put on your socks, then you put on your shoes, right? But how do you take them off?
Socks.
Right, the opposite order, right? So the proper. It's probably more with this. If you think of inversion, it's easier to see the meaning of the saying. So, if you think of, let's see here. It depends on how you want to think about it. If B, I put on my socks, and then A, I put on my shoes. Then I take off my shoes, and then take off my socks. Sock shoes, yeah. Of course, no one says you have to wear one pair of socks, but the rule remains the same, if you think about it.
Is that a property we have to know the inverse? Or is that going to follow along with like the traces?
Yeah, you should know that also for just function composition. If you have the inverse of a composite, it's the composite of the inverses in opposite order. This is actually not just a matrix multiplication thing. This is a more general function theoretic thing. But that's a conversation we really ought to have in Math 200. I think you had 250, but
So if you had like
transition to.
quantity
Oh wait, you're messing with me. Okay.
A,
Okay.
B transpose C, would that transpose like?
Oh yeah, it's the same. If I
It's like the same principle
Yeah.
versus the transpose.
same pattern. Yeah. Indeed. You can prove it. You can use induction to prove it for an n-fold product under transpose. Yeah.
And then say in the first part, E were transpose.
Yeah. All right, so let's get back to the basics because most of this test is not about these things. It's much more about what we did earlier in the course, right? So just to get back to the basics, what are the basics? Well, we need to think about, do you know how to carefully define continuity of a function of several variables, right? In a normed linear space. Can you define the Fréchet derivative of a function from one normed linear space to another, right? Do you understand how we take partial derivatives in a normed linear space? Do you understand how we can piece together the differential from the partial derivatives, right? If we go back to the solution, and so later in here I give you, oh man, Lorenzo, seems to be a theme this week. I don't know. I just keep taping all my classes this week. It's not ideal.
You should just stop at
Stop having tests. Yeah, that seems like Well, make my classes more popular.
So they give me
So, do think of, I mean, this was a homework problem, right? How does a differentiable implies continuous? There, the nice way to do this was to define the Fréchet quotient as R sub f, and to realize that R sub f goes to 0 is equivalent to the differentiability, but then you can solve for f of a plus h in terms of the R sub f and such, right? It's kind of the theorem of Carathéodory written in as much as we can write it here. I mean, I still don't think I found the proper version of the theorem of Carathéodory in our current context, but anyway. You should make sure you know the statements of the inverse and implicit function theorems, right? And how that connects to the method of differentials, right? Essentially, your ability to solve for a certain subset of, the differentials of particular variables corresponds to your ability to actually view those dependent variables as functions of the remaining variables. That, in a nutshell, is what the implicit function theorem says. I would like you to understand the intuition of the proofs that we went over. That would be good. Let's see here. Can you derive the method of Lagrange multipliers? What am I talking about there? Do you guys know how to derive the method of Lagrange multipliers? So what's the starting point? Right, there is a solution. First of all, before even that, there's some objective function that we want to minimize or maximize, right? And then there's some constraint, or constraints more generally in this course, that we're trying to find the maximum, the extremal point with respect to a system of constraints, right? So the, sorry, I gotta do this again. So basically, you have your objective function f, right? It's a function of x1 through xn, and then you have constraints g1 of x1 through xn equals to, say, c1. And let's suppose it's j and j runs from 1 to, say, p. Suppose you have p constraints. So that makes the constraint surface what? Or constraint manifold. We can call it that. It is a, what, an n minus p dimensional, right? Assuming what? All right, the constraints are independent, or equivalently, this function big G has the rank of G prime equal to P at all points in the solution set. All right, so in that case, we're looking for the maximum that F takes somewhere on this constraint manifold. So let P be that maximum, place where the maximum is, so let this be the point f of p equal the extremal point, extreme value, right? And then how do you derive the Lagrange multiplier condition is a necessary condition for this. That's the method, right? You just consider a curve. Consider an arbitrary curve through there, say gamma, right? And we assume that gamma of 0 is equal to p, right? And that g of gamma of t is equal to c vector, right? In other words, it satisfies all p of our constraints, right? That means that the curve is actually on the surface. So this condition differentiates to give us what? G prime of gamma of t times gamma prime of t is equal to 0, right? Which actually says, if you unwrap that, that says that the gradient of g1 of gamma of t dotted with gamma prime of t is equal to 0. Well, not just 1, but j equals to 1 to dot p. which is to say what? Which is to say that if you plug in t equal to 0, we have the gradient of gj at p dot gamma prime of 0 is equal to 0, right? So gamma prime of 0 is an element of the tangent space. Well, excuse me. Yeah, gamma prime of 0 is an element of the tangent space at p of m, right? Because it's perpendicular to every normal vector. But we also have something else, right? In fact, that's not true just for t equal to 0. That's true for each time along the curve, if you want to think about it. Now, what makes this point special is not so much g, it's f, right? So on the other hand, we have that we can look at f, well, let's say h of t, right, is f of gamma of t, right? Notice that h of 0 is equal to f of p, which is an extreme value, right? But h is a function from r to r, right? I should emphasize the objective function is real valued, you know? So that means that h prime of 0 also has to be 0 by Fermat's theorem, right? Back in Calc 1. But h prime of 0 is also f prime, well, getting to the point, it's the gradient of f at p dot gamma prime of 0, right? Which says that the gradient of f at p is an element, yeah, the normal space, the normal space at p to m. So this conclusion isn't terribly the point. I mean, that's not really the point. I don't know, I guess in some sense this isn't entirely necessary if you already know that the normal space is what? I mean, I guess the thing to take away from this isn't this. What should I really take away from this? Yeah, that these, thank you, that these are in the the perp, which is the normal space, right? And also that since gamma is arbitrary, the normal space at p to m is the span of the gradient of j at p, j equals to 1 to p. So in other words, anything in the normal space we can build from these gradient vectors. And so from those two ideas, we get that the gradient of f is equal to lambda 1 gradient of g1 plus lambda 2 gradient of g2 plus plus lambda p gradient of the pth constraint function. So that's a necessary condition for an extremal point, assuming that we have a smooth constraint surface and the objective function is not weird. I mean, you also need that the objective function is differentiable. If you had a differentiable function, if you had an objective function which was like discontinuous, then you'd have to do other things, right? Just like in Calculus 1, we teach you a nice theory of minimization and maximization for continuous data. But at discontinuities, you always have to look at the pieces, and it's just a mess. That's the proof I'm talking about. We did it in class before, right? So I also want you guys to be able to find, tangent spaces and normal spaces to manifolds that are either presented implicitly or parametrically. I keep kicking this thing. Let's see if we can't find a good. I give you a good list. I think of these ones are, I know you guys' time is limited, so if you're going to rework homework problems, I would urge you to focus on these particular ones. I think these ones have these are either simple proofs or computations which I think are core to this course, all right? So I think these are, hopefully will keep you away from the more distracting